Hello viewers. So today we are going to discuss about a topic, but before starting our today's topic I would like to introduce myself. My name is Vikram and today we are going to discuss a very important topic from the perspective of board examination as far as state board examinations are concerned. So basically it is a topic that comes under applied part of physics. So you can divide physics in two parts. One is fundamental physics and other one is applied physics. So basically applied physics is all about the devices that we could make based on the theory that comes from fundamental part of physics. So basically we have a device with us today that is very important, and it is asked repetitively in your board examination, and you can verify it by examining previous year question papers. So basically what we have before us today is galvanometer. Galvanometer is a device which is used to measure voltage and currents across a circuit. And one thing you can put into your answer that these currents are normally within the micro or milliampere range. So basically it is used to measure small amount of current. So the basic principle behind the working of the galvanometer is it consists of various parts as every device has. So it is a top view. Top view basically, this is the front view. If I look this marker or this chalk holder from the top or above, then what I have seen from that is called the top view of this chalk. So basically it is a top view of device. So it consists, as you can see, these two permanent magnets. One is north pole and other one is south pole. In between them we have a iron core, soft iron core, which is used to amplify the effect of magnetism, and the coil that is wrapped upon this you can say iron core. This coil is made up of copper and it carries current. So basically we have three parts. Now the shape, why this is spherical or circular in shape we will discuss, or cylindrical in shape we will discuss it later in this lecture. So we have a pointer attached to a spring. So these are things that you have to mention while answering this question about galvanometer. So these are the points. So this is the diagram or geometry of this particular device. This pointer attached to the spring, and it will indicate a reading that is mentioned on this scale. And this scale, one thing that is you have to keep in your mind, that this scale has a neutral point which is lies in middle of the scale, so that if this pointer points in the direction, then you can have a particular direction of current flowing through the circuit, and if pointer point in this direction, then you have other direction of current. As you know, circuit can have two direction associated with it, while we are talking about the as far as we are concerned about the direction of current. So this is one direction and this is the opposite direction. So now comes to the part, how does this device work? Basically it works on a principle or on a fact that when a current carrying coil placed in a magnetic field, it experiences a current carrying coil which is wrapped upon this soft iron core. When placed in a magnetic field, it will experience a torque. So based on that torque, how much torque is produced, based on that torque we can indirectly calculate the current flowing through this coil. So it is a type of arrangement through which, by measuring the torque, we can measure the amount of current or voltage across between two particular points in a circuit. So I hope it is very well understood by you. Now the thing is, second thing that you should mention in your answer writing, that why we have this circular or cylindrical magnet. They need to provide a uniform and radial. The point here to remember is radial magnetic field. Radial magnetic field, why we are using radial magnetic field, we will learn later within few minutes. So when a current I flow through this coil, it experiences torque, which is given by torque. General or general is symbol. Torque is given by m. Here m is magnetic moment and b is magnetic field that is being produced by these magnets. So m cross b will provide you the torque that will be experienced by this coil. Now from our previous, that is need not to be mentioned over here, but it will comes out to be tau is equal to n IAB into sin theta, but I do not written it here because here the radial fields comes into the play, and radial field provide every time that angle between area vector. Suppose this is the single turn of a coil that is wrapped around this iron core, then area vector will be, area is the total, suppose this is the length or breadth. Now area of this coil is considered to be A cross B, and direction according to the right hand thumb rule. So this area vector and magnetic field always have a angle 90 degree in between them, so that we can take always sin theta as 1. So this formula comes out to be NIAB. Here n is the number of turn that is here, and I is the current flowing through the coil, A is the area, and B is the magnetic field. So from now what we have, a spring. This is a spring that is going to tackle or counter the torque experienced by this pointer due to the current carrying coil. When subject to a magnetic field, it will experience a force. To counter that torque, we need to have a spring. What is the utility of this spring? This spring will provide counter torque for steady deflection. Otherwise you will have a very random and very fast reflection or deflection when this coil is subjected to a magnetic field. So to have a balance or steady deflection, so that we can measure the amount of current, we use this counter to counter this torque. We use this spring, and the torque generated in this spring will be K into phi. Here two terms, K into phi. Phi is the angle of deflection. Suppose we have a particular deflection or angle of deflection, then we will get phi from that deflection, and K, this is the spring constant, which is unique to every spring, or it is mentioned by manufacturer when we buy or purchase a spring for a particular K. So basically it is attached or a physical property of a spring. So we have counter torque, that is K phi. For a steady operation, it must be equal to the torque generated due to current carrying coil due to magnetic field in a current carrying coil. So K phi should be equal to NIAB. By comparing these two equations, we can have a further derivation or further simplification over here. Phi is equal to, this is basically just rearrangement of terms. So phi is equal to NAB over K into I. So here we can see terms in the bracket are constant, and it is fixed for or constant for a given galvanometer, because N, the number of turns, you can't change it. Once you manufacture the device, area of coil, you can't change it. These magnets are permanent, and K, as I said, it is always mentioned by manufacturer over a spring that you purchase from or a manufacturer purchase from market. So basically these things which are written in bracket are always constant for what is variable, that is I. So basically this is the deflection. On having a particular deflection, we can estimate the value of I. So you can see here. Now to have this device or to make this device work as a ammeter or voltmeter, we need to make some changes to this. Let's see what are these changes and how we can turn this galvanometer into a ammeter or a voltmeter. Thank you.